Hello, welcome to the second part of the cache coherence protocol discussion. Here we are going to actually see an implementation of cache coherence protocol. Couple of them we'll see. Most popular one, MSI and MESI. And then direct based protocol, I'll just touch upon it and we are not going to be covering it in detail or trying to understand the intricate functioning of directory based protocol. It's only an overview. Now, just to tell you why we need a cache coherence policies. Okay, where is the cache coherence coming in? First of all, when you have multiple cores and they are accessing a main memory. See, assume a main memory is here. It's not shown here. Okay, multiple cores are accessing the same common main memory. In this situation, where you have multiple copies of the same data available on each of those private caches of those cores, how are we going to make sure that the data which is there in the main memory as well as in the multiple copies of those private caches are kept in coherence? That means we see a coherent value. It doesn't matter where you are reading from, whether the same copy is available in some other cache or not. The behavior of the processor software running on each of those cores should be deterministic and it should be as intended by the programmer. So we are going to see there are two ways in, and basically the coherence can be maintained. One is write update. That means we are talking about write. Why? Because when you have multiple caches and multiple cores are accessing a data, and if all of them are using the data which is available in the main memory only for read purpose, there is no issue at all, because nobody is changing the data and everybody is reading from it. In that case, there is no issue in terms of maintaining a coherence between multiple copies, because they are going to have same copies on all the private caches as well as the same value is going to be in the main memory also. So read operation does not cause any issue at all. That is why we are going to talk about write operation. Now we can handle the write operation of any core to a particular common data which is being shared by or which is being accessed by multiple cores. We can handle it and maintain the coherence if every write any processor is doing. Suppose this processor is writing on its own copy and this also is writing, and this may also be writing into some other copy of whatever it has. Now you can imagine that the same copy is maybe possibly available or maintained on other caches also, right? There is nobody stops you from having a copy of the data on some other cache when another processor is using it, because there is a possibility that cooperating processors may be running on multiple cores and they may be using the same common data which is available on in the main memory, which is being accessed by multiple cores by bringing them into their own caches. Now suppose we have a mechanism by which if any processor is writing into a particular cache line, it is changing it, making it dirty, then what you do is you also have a mechanism, additional hardware which says that, hey, this same copy is available on some other cache also, the same block. Then what do? You update the value which is being maintained by other caches also. Okay. And if it is a write back policy, then maybe you will later on you will reflect it in the main memory, but you are making the every copy of the same data is having the same value. As soon as one processor is changing the value, the same copy, if it is available on some other processor, you change it there also. So this is called write update policy. In this way, we are making it coherent. And then later on, when the particular block is getting evicted, it may be written into the main memory. Doesn't matter. But now all the cores which are having the same data is seeing the same value. Okay. Now another way of managing it. Suppose you have uh, multiple copies which were there, and then one processor is trying to update the data. Then what you do, you want to make sure that the same copy is not in multiple places. You immediately say, go and invalidate them. That means it is as good as they don't have it. This particular cache line was there here, but once one person is writing it, the other core is having a copy will be made into invalid state. That means if the processor wants to access the same D, okay, same data, it will find that it is not there in the cache, and then it has to go to the main memory, okay, or it will ask for the other core to give it and make it, no, I own it, and then you make the other one invalidate. So there are two ways you can make sure that the consistency is maintained. Either copy, if multiple copies are there, update all of them. If one core is changing it. Another one is, no, make sure that only one processor is owning it and all other processors are are not given the access to that variable or that block. Okay, always think the caches are operated in terms of blocks. No, not in a particular byte. It is in whenever we are saying a particular cache entry or any changes, it is at the block level. Now let us look into the write update policy. Okay, that means you are updating all of them. It's a greedy policy. That means whether other cores are using it for only infrequently or frequently, doesn't matter. Yeah, as long as the copy is there, you are going to go and update it. So maybe the possibility that only this core is continuously changing it. All these cores, though they are having the copy, they are not even using it. So maybe that process is not running. But still, because the cache copy is there on those other multiple caches, you have to go and update it every time. So what is the problem in this? Or as data is updated in one of the local caches, it copies in other caches are immediately updated. That's what I said, right? Copy in the main memory may or may not be updated. Depends on the write back or write through. Suppose if you are having a write through, then main memory is also updated. If it is a write back, maybe when these blocks get evicted from their cache lines, it will be updated. The issue here is immediate data migration, unnecessary traffic in case of infrequent use shared data. So infrequently used shared data. What I am saying is it is being shared, but maybe other cores are not actively using them. Just because it is there in their cache line, you go and update it. Whether it is required or not, you don't know. So this kind of a greedy policy actually creates lots of traffic on the uh, this bus. We are calling it as a snooping bus, and then we go and update it on all other caches also, entries also. There is a special hardware which keeps track of which are the blocks are maintained in different caches. Okay, and if it is a write through policy, then you will see write back or write through is always with respect to memory. Write update or write invalidated is with respect to the copies of entries in the other caches. So you need to know the difference between these two. So write through or write back is with respect to a cache copy and the memory, and write update or write invalidate is with respect to the multiple copies of the same data available on different cores. So if you are using a write through policy, the write update coherence policy will complicate the issue, because all the changes that even if one processor is changing it, all of the copies in the individual private caches are updated as well as in the main memory. So it's a too much of a overload. So cache controllers, this is all done by the cache controllers, have to accept write requests. So we need to have a provision that the cache controllers not only taking the value, read or write accesses from the CPU, it has to get the write request from coming from the other cores in the same process, in the same SOC, okay, or in the system, okay. Now, what is write invalidate? Whenever one processor is accessing it, there may be multiple copies available, but once one guy changes, then you make all of them invalidate. Okay, so it's called a lazy policy. What do you say? Yes, data is updated in one of the local caches, all other copies in other caches are immediately invalidated. I'm talking about the same entry, the same block, available on other caches. Okay, there is a possibility. So while not updated in main memory, so again, if it is a write back, main memory is still out of sync with the copy in the local caches. Data is provided by the updating processor cache for the read request from other processors. So in this case, what happens is you are invalidating them. But what if one core wants to read from it? Now, if it is a write back policy which is in place, that means main memory is not having the updated data. One of the processor is owning it, and it has the information. So if any read request come from other core for the same block, the main memory cannot provide you, but the processor which is owning it only can provide. So the data is provided by the updating processor cache, okay, whichever is owning it, that read request will be handled by them. So the cache controllers have to accept invalidate command from coming from other caches, and then read commands coming from other places. So this is what we are going to go in depth, okay, to understand it, because we have already ruled out the write update policy as a cache coherence policy, because it has lots of traffic going through different caches. So we are going to now concentrate more on cache invalidate policy. Okay. Now this MSI and MESI fall under the cache invalidate policy. Okay. Remember, this is about the cache coherence. Okay. Now, how do we implement it? The practical multiprocessor write invalidate protocol, which attempts to minimize bus usage, because we are minimizing it, because every write we are not going to go and write it on all the copies. We are only localizing the writes only to the local core processor, and others may, if they are reading it, we will provide them. But we are not going to keep on updating every copy that is available in the entire world, right? When I say entire world, means the other cores in the processor, in the system. It allows usage of write back scheme. Okay, we are going to use the write back only here. That is, main memory is not updated yet, but the cache line is dirty in the one of the processor cores, local copy. Now, how can we do this? This is possible only if you do a snooping on the bus. What is the interaction happening? So cache line changes state as a function of memory access events. So a particular cache line sitting in a particular core, its state can change based on the event which is happening in the bus. So there is a snooping bus which is watching what is happening and what is done by other cores in the system. Okay. Events. What are the possible events? Uh, the events could be due to local processor activity. It could be a read or write happening from the local processor. Okay. I'm now talking about a particular block or a line in a cache inside a particular private cache of a core, and we are going to maintain some state for each of those blocks, and those states of those blocks will vary based on the operations coming from the local processor, which is read or write, or due to bus activity, which is called snooping. Snooping means you are watching you know quietly what is happening on the bus. I am owning some block, and related to that block that I have in my cache, are there any activities happening in the bus from other cores? So snooping is activity sniffing on the scheme by which a coherency controller, a hardware, is in a cache, monitors or snoops the bus transaction, and its goal is to maintain a coherency across the distributed shared memory system. See, because remember that it is all because of multiple cores accessing the same common memory, and the processes running on those cores are updating the value. So the cache containing a coherency controller or a snooper is called a Snoopy cache. This scheme is introduced by Ravi Shankar and Goodman in 1983. Okay, so just to summarize, we are going to look at the write update or write invalidate. There are the two things I told you. Write update means it is updating everything, which we are not going to bother about, because lots of traffic is there on the bus, as well as we are going to change every any change happening in one place, we are going to make changes to other places. Here we are going to use the policy which is called write invalidate, and we are going to implement it using some protocol, and for that we need a snooper hardware, or one which is monitoring not only the transactions which is happening between the CPU and the cache, it is also seeing whatever cache lines I have in my cache, those blocks, are there any accesses happening to those blocks, any changes happening to those blocks from the accesses initiated by other cores in the system. Okay, so it's called snooping, and because of that, the cache line states are going to be modified. Now, MSI is nothing but three states of every block in a cache, which are modified, shared, and invalid. Okay. Now let us understand each of those states. I am showing you a cache 0, which is having a data 1 means it's not a single byte or a word. It is a block of cache line block. Okay. It is always in terms of a block within the cache. So they can be in any of these three states: invalid or modified or shared. I am talking about one particular cache inside a code. There may be another cache within another code. So those blocks may be the same blocks which is sitting there, or maybe they are using totally different memory and then they are having it. Okay. So the issue comes only when the same data which is residing in multiple locations inside the different cores. It can be in anywhere in that particular cache. Okay, please remember, the based on the mapping function which is being in action, the actual location of those blocks within the cache doesn't matter. As long as it is there, it is understood to be there. And you know that, how do you know that the same block is there in multiple caches? Because they either map onto same logical address or physical address based on whether logical cache or physical cache, but the same address and will be there. Okay, the content of that addresses will be there. And remember, we are assuming that all the cache in the system are having the same block size, and they all have maybe could be that they have same mapping function also, but it's not very compulsory. But block size has to be same. Now, what are those states of those? Each cache line can have one of three possible coherency states. We are calling it as a coherency state, these three states. Modified. What do you mean by modified state? The line, a cache line, is modified and it is inconsistent with the main memory. Okay. Cannot be cached at another course. Now, we are saying that if you are following this MSA protocol, there should be only one owner of a particular cache line. Owner means a owner who is writing into it. You cannot have multiple writers into a particular cache line. So if suppose some cache line is there sitting inside a particular processor, is private cache, and the processor is writing into it, that means it is modifying that particular cache line. In that case, that particular block or a cache line is in the modified state in that particular cache, and there can be only one place where the cache block can be in the modified state, because we cannot have too many writers into the same block because there will be inconsistency. So we are saying that we are simplifying it by saying that if somebody wants to write into a block, it will be in the modified state, and only that particular at particular time only one copy of that block will be in a modified state in any of those multiple cores in the system. He is a owner. Now that means what? That particular CPU is accessing it and modifying it, that copy. Now, is it in sync with the main memory? Need not be, because if that particular cache is following a write back policy, the modified content is only available in that particular core who is owning it right now as a in the modified state, and main memory, the same a block of content in the main memory may be out of sync with the content in the cache. Now, there is a possibility that a particular block is in a shared state. It is, that means that it is unmodified. That means the content of that block, which is in shared state inside a particular core, is in sync with the content in the main memory. They are same. There is no difference between them. And that particular block may not be in one place. It could be in other cores also in shared state. So you may find a particular block in a shared state on single core or it could be on multiple cores, maybe one or many, but all of them will be in shared state. Nobody is actually modifying it, and it is also in sync with the main memory content. So if everybody is reading from them, no issues. You can have multiple copies of shared block in each other code, and that can work. Note that in this state, it is not clear whether there is only one copy or many copy. It can be shared, can be maybe one copy also, or multiple copies can be there. If a particular block is invalid, in the sense a line is invalid means it is not mapped to anything. In that case, the line is not available in the cache. Okay, it means no valid data is sitting inside. So you don't have to do anything action. So now let us understand a read operation is coming from the CPU on a block, and now that block can be in any state. Okay, now imagine I have a line within the cache, and I am getting doing a read operation to the block which is in the modified state. That means what? That modified state means that block is in the owned by this guy. Maybe previously it has modified it, and it is only one copy which is there in the modified state in this core, and there is no other copy available on other cores, and the main memory may be out of sync because of write back policy, but now it is asking for a read operation. So you can give the data immediately, right? Where you are having the updated data with you in the modified state, and right now you are performing a read operation, but previously you did a write operation. That's why that block is in the modified state. That means it is in the dirty bit of that particular block is set. So no problem. If it is in a modified state when you are doing a read operation from the CPU, I am talking about the CPU core operating on the block. Now suppose if I have a line which is in the shared state, and then the CPU is now making a read operation to that particular block. When I say that, the same block may be available on other core also, and if it is available, it will be in a shared state. And if it is in a shared state, the main memory is in sync with the content in the shared state. And when you do a read operation, do you have to worry about anything? You can just give the data what is there, because it is up to date with the main memory, and it is same as what are the copies of the same available on other caches. So my local CPU, if it is asking for a read operation, I can give the data without any problem, right? Now, if the line is not in the cache, then this read will be a read miss. It is in invalid state. So the CPU is asking for a particular block. It is in the invalid state now. That means what? That block is not there in the cache. You will get a read miss. Now what do you do? Then there is a possibility that it is not anywhere there also. Nobody else is having it in any of their caches. That means this particular block is not there in any other cache. It is only in the main memory, the content. Then you can take it from the content, main memory, read it, and then keep it in shared state, because you are asking for a read operation. You are not modifying it. So if it is not in another cache, no, first read it from the memory and keep it in shared state, because you are only doing a read operation, so you can keep it in shared state. So that's why I meant that if it is in shared state, it could be in one particular cache only, in only one core only, or it can be in multiple places also. In this case, it is invalid in all other places, means you are reading for the first time maybe at that moment, and the block is coming to this particular core, and it is doing the read operation, and it remains the shared state. Now if it is in another cache in a shared state, suppose if the same block is in other cores also, and they are in a shared state, and you are not having it there with you, now what you can do, you can read it from the memory, because memory is in sync with the other copies of the caches. So I read it from the memory and keep it in shared state, because you have to keep it in shared state. Now what is the other possibility? If it is in another cache in the modified state, now is the complexity. Now you are looking for a block for a read operation, and it is not there in your own cache, but it is available in some other cache in a modified state. That means what? The first thing what it should strike you is it is in another cache. That means it is writing it, that other processor is writing into that particular block, and it is in the modified state. That means it need not be in sync with the main memory, because write back policy could have been there, and it may not be updated on the main memory. So only that particular core which is owning that particular block in the modified state, keeping it in a modified state, is recently modified, or maybe it has modified sometime back, but it is having the latest data available there. Now there is no point in asking for the block from the memory, because memory doesn't have it. It doesn't even have the updated value. So what should you do in this case? You should ask the other core who is keeping it in the modified state to write back the value now into the main memory. Now, what should be the state change for the core who is having it in modified state? It has kept it up to date with the main memory, and the same copy can be given to this guy who is first time asking for it. So it will come to the this core. Now you cannot allow that guy, the other core which is keeping it in a modified state, to remain there, because only one person can have it in a modified state. Now you are giving the same data to another core also. Okay, what do you do? Make it shared in other place, so that that core knows that I am not now free to update it as and when I want. It is in shared state. That means somebody else is also having the same block with it in their cache. It can be one or many. So what do you say? Write back the new data from the cache, the who is having it in modified state, and make it shared state. Now you do say that you are now going into a shared state. Okay, this should be shared. Okay, shared state. Afterwards, the line may be obtained from the main memory, from the writer cache, and the state is made as shared. Now here also you make it shared. Okay, so both of them are now shared. Okay, you cannot have more than one copy of the same data in the modified state. Only one core can have it in modified state. If it is there are multiple copies, then you make them all shared. So this is the read operation. Now think about write operation. Now when you want a write operation to be performed by the CPU to a particular block, there are other, again, many possibilities are there. Okay, a simplest thing, let me start with the simplest one. If the line is in the modified state, that means what? The already, it will be the right operation will be a right hit. Okay, it will not be a right miss. Okay, if it is an invalid state, then it is a right miss. But right now I am assuming a state which is called a modified state. In that case, you are already having it in your cache, and you are only owning it because you have modified it. So right operation will get a hit, and you don't need to worry about it, because you are the only person. The CPU is only having it, and mother cores are not having them. And you can actually now take it from this particular um, cache and give it to the CPU. No, sorry, you write it. Okay, you allow the CPU to write into it, modify the data locally. Fine. No, you don't have to do anything with the other caches, because they are not even having it. Okay. Now, if the line is in shared state, that means what? It could be that this particular block is only in this block cache, or maybe it is there in other caches also, other course caches also. But you are now asking for a write operation. That means you have to now change it to modified state, because you are going to modify it, change it. Now main memory is in sync with the data, but you are, this CPU wants to write into the cache block which is in the shared state. Then you should change it to modified state. Now it's not enough that you do only this modified state, because you have to also make sure that other cores who are having this may be having it or may not be having in this case, but if they have the same copy in the shared state, then you have to make them invalidate. So notify any other potential owners of the line. It's not a owner. Owner has a read up for the reading operation of the line of the that their data is not legal anymore, because this guy is changing it. We are allowing only one processor to change it. So you make that invalid, and also change that state to invalid. One or many or none. Okay. Modify the line locally. Any change is to modified state, and then change the state to modify. Now you change this value of this, whatever the CPU wants to write it, let it do it, and make it modified state. Okay, that means what? Now only this particular core which is having it in shared state has become a modified state, and it is owning it now. All other core, if they are having the copy, they are all made invalid. and the memory may be out of sync with the content which is being written into the by this CPU. If the line is invalid and the CPU is saying write operation, then if it is invalid, it's going to be a write miss. Now, when you are having a write miss, you are trying to write into the cache a block which is not there in your cache. Now, what are the other possibilities? It's not there anywhere, then that is the simplest logic, okay? Or it is there in a modified state somewhere or shared state somewhere. That's all, okay? It could be one of those three states only, right? In other places, if the line is in another cache in the modified state, now I'm taking always a complex scenario where this particular core wants to modify the data, whereas the same block of data which is there in another cache in the modified state. That means that guy was changing it. Now, what should you do? You need the latest data which is written by that cache, that core, on your cache line before you write into it. At the same time, you should also, make sure that the other core no longer thinks that it is owning it and modifying it, can modify it. So what you do, you ask the other core which is having it in the modified state to write the value into the cache. Need not be writing into the cache because modified state can be out of sync with the main memory. But what you do when you are transitioning from one modified state to the from modified state on one core to another core, also in the modified state, write back the result into the memory, okay? Because whatever changes are done by the core has to be reflected on the main memory. Do it and make that entry invalid, because you are going to give this block to this another core for the write purpose. That means this is going to be keeping it in modified state. So two cores cannot have the same block of data in a modified state, only one. So the person who is having it, the core which is having it, is made it into invalid, and if the okay, and you give it to this modified state, okay? Now, if the line is in any other caches in a shared state, what do? You are having it in invalid, but other cores are having in shared state. Then what does it mean? It is in sync with the main memory. So the line is in another shared state. Notify those previous owners of the line is no longer no legal. You make them invalid. Okay, all of them make it invalid, and then write the data, which write the new value in the line and change it to modified state. Now, what do? You get it from the content has to be invalid means you have to get the value from the memory and then modify it. Whatever operation you are performing, you modify it. So this is what is done by the MSA protocol. So this, we talked about read hit and read miss and write hit and write miss. And when the same block is in modified state or shared state or invalid state. Now, one thing if you noticed in the MSI, the shared state of a particular block is imprecise. Imprecise in the sense it could be there in one of the core which is having it in shared state, or it can be many, one or many. That is not very clearly identified. So to avoid that confusion, we are bringing in another state, okay, in the MESA protocol, that it is exclusive. Okay, so I will tell you what is the advantage of this. A new state exclusive is added. This cache line is guaranteed to be present only in the current cache. Okay, so when it is in exclusive state, it is only in the current cache. There nobody else is owning it. But see, if it is a modified state, you know that it is owning it for the write purpose. If it is having it for a read purpose and it is only available in one particular core, you keep it in exclusive key. Once a particular cache block is in exclusive state in a particular core, that means this particular core is using it for a read purpose. Its dirty bit is not set, and the content of that particular block in main memory is in sync with what is there in this. And one more condition is the same block is not available in anywhere in another core. So it is in a exclusive state. Write operations to an exclusive line. Now, when you do a write operation to the exclusive line, you know very well that it is not in available anywhere. So you don't have to go around broadcasting saying, hey, I am going to modify it. Please, invalidate all your entries. You don't have to do at all because you know that you are only owning it. And you don't need to worry about main memory right now, because if you are having a write back policy, you don't need to worry it. Now, what will you do? You can just write operation to the exclusive line need not interconnect with other caches. You can just own it and make it modified and keep writing it. Okay. From exclusive to write up, modified state, you can do it faster without going to other caches. So now, what is the motivation? Consider the write operation now in MSA protocol. Now, suppose if you are in MSA protocol, you don't have a exclusive state there, and the block is in shared state. What do? You don't know whether you are only owning it or multiple cores are owning it. So when you are writing it, you want to change it to modified state. Then you go around informing everybody, even though they are not having it, saying that hey, I'm going to change this block to modified state. So please invalidate all your entries. You don't need to do it in the MESI protocol, whereas in MSI you need to do that. So it's an unnecessary uh, transaction on the snooping bus. Need to interconnect to other cores. So we are avoiding that particular thing in MESI protocol. So any cache line can be in 4 states. Okay, the 2 bits are used, MESI. Now let us understand what is modified state. If a cache line has been modified, it is modified state, it is in modified, that means this core is doing the write operation. It is different from other main memory content because it is write back policy is because always we are doing write back only. Write to doesn't have to do all these things. Okay, you can assume that it is MESI or MSI protocol is coming because of write back policy. Okay, it is out of sync. Write through policy anyway, no problem at all. Right, every copy is up to date always. So you don't need to worry about MESI or MSI. So it is assumed to be write back, and this is the only cached copy. Okay, this is the only fellow is having it in their own cache, and it is for the right purpose, that is modifying purpose, and dirty bit is set for sure, and the memory is out of sync. What is exclusive? It is for the read purpose, and it is the only core, only one copy is available, and it is for the read purpose, and there is no other copy available on other cores. Okay, and the value of this cache line is same as main memory content. Okay? These two are very important points to be noted. What is shared? Shared means you are using it for read purpose, and it is for sure is available in other cores, because here exclusive is there. That's why I'm saying shared means another copy is there somewhere else, and both are in sync with the main memory. The shared copies are also same, and the main memory content is also same. Both the cores are using it for read purpose. Okay, invalid, no issues. That core itself, that block is empty block. Okay, what do you maintain anything? This is simple. Okay. Now, operation can be described informally by looking at the action in local processor. Let us see, what are the operations that you need to do. The local processor do read hit or read miss or write hit or write miss. So let us go one by one and understand it. Very easy. We can have a transition diagram which I will show it at the end. But right now, without the transition diagram, let us try to understand it by assuming that what are the states a particular cache line can be. Now, can you tell me if suppose you can think about it, you can pause the video and think out of these 4 states. Okay, out of these 4 states which are shown here, which is a state, which are the possible state that you will find a particular block in a local CPU copy if it is a local read miss, sorry, hit. If it is a hit, that means what? The block is there in the cache, right? And the state cannot be invalid, but it could be any of the other 3 because it is a read hit. It's a read hit. That means there are other 3 states which are possible. The same block can be in 3 different states. Line must be in MES, not in I, because if it is invalid, you wouldn't have had a read hit. It would have been a read miss. So now think of a read hit for different states. Okay. Now this must be a correct local value. If M, it must have been modified locally. Okay. This must be a correct value. Suppose if this is a correct value, you are getting a read hit, and if it is M, that means it has modified it recently. This processor only is modified, and it is the only copy available in the system. No other cache is having this block anywhere else. So you can provide the data which is available in a local cache. Simply return the value. No state change. Okay, it's a read hit and it is in the modified state. Now there is a possibility that you have already taken care of M state. Now, if if no other copy in caches, that means what? It is only hit means, it read miss. Okay, it's a local read miss. Now I talked about read hit, local read hit. Okay, and then we only talked about M, and then now we are going to talk about read miss. Okay, if no other copy in caches, and it is not here also, what do you do? It's all invalid everywhere, and here also invalid. Read miss means it's invalid. You have to, where do you take this value from? Main memory. Processor makes bus request to memory and takes it. Okay, and now you are, if it is no other copy in other caches, that means you are reading it for your own. You are the only first owner now. That means you have to keep it in exclusive state. That's why E. Now another possibility that one cache has a E copy. Okay, uh, that means what? You, one particular core is doing a read operation. It's a read miss, whereas the same cache block is there in a exclusive condition in some other core. Then what you should do? Now you, one more person wants to do the same, wants to read from the same block. That means it is going to be in shared state now. Okay, so exclusive state on the other core also becomes shared, and you are also going to have it in the shared case state, and you can actually take it either from main memory or from the adjacent cache, and you take it from the memory. Snooping cache, now what is happening is you are trying to take it from the memory, but snooping cache looks at that, okay, I have a copy there in my shared copy, e copy, exclusive copy. It is in sync with the main memory, but it will provide you, puts the copy value on the bus, memory access is abandoned, and local processor caches the value. Now actually the data is going to come from the adjacent core, because which is having a e copy, and this guy wants to read the data. Now both will become yes, and the value which is there in the cache block comes here. Okay, main memory is not touched because anyway it is in sync. You don't have to go to the main memory. Getting it from the neighbor cache is easier than going to main memory. Both lines are true, yes. Now again, look at the read miss. Several caches are having it in share copy. Now one more guy wants to read it. Now what is very simple, right? You can take it from one of them, don't have to go to the main memory, and keep it in shared copy. You are also joining the gang who is owning this main block, not owning it for read purpose. Okay, owning it for read purpose. So you keep it, and a processor makes a bus request, but you make a bus request, but snooping cache controller will say that, oh, I have a copy, I will provide you. One of the caches, no arbitration will happen, and they will give you memory access is abandoned, and the local process cache's value, and all of them will be in local copy is S copy. Others are anyway no state change in others because they are already in shared copy. You make one more shared copy. So copies remain yes. Now another read miss. One copy has M copy. One local cache, on another cache is having a M copy. That means modified state. That means it has modified it and it is keeping it there. Now, when you are having a read miss, you are going to use it for read purpose. So you can keep it in multiple caches in a shared state, but you have to make sure that the main memory is updated with the modified copy. So what do? You take the processor makes a bus request. Now it is abandoned. Snoopy cache catches that thing, puts the copy value on the bus. Okay, it is modified copy is there in one of the processor, so it gives that value to the core which is modifying, asking for it. Memory access is abandoned by the core which is making a read access. Okay, local processor caches the value, local copy tag to yes. Okay, and source M value copied back to memory. Please remember, in a shared state the memory should be updated, it should be in sync, and both the copies, now whoever is owning it earlier, it was in M copy, it becomes S copy. Now yes, shared source. Okay, you make that M to S, and you also read the value from the neighbor cache and make it S, and update the main memory. So all of them are in now sync. No, now two processes will be in shared state in this case. Write miss is done, all possible combinations. Now write hit. You can strike, write hit means what? It is already in the cache. That means you are doing it for the right purpose. Okay. Now line must be one of this. Invalid is not allowed. Please remember, write miss doesn't mean that earlier it was written. It may be the first write, it could be. So you may be having the cache block for read purpose, or you might have already written into it, already the block having a dirty bit or may not be dirty bit is not set. Okay, then both the possibilities are there. This right hit could be the first right hit, or it may be a second or any number of right hit. In that case, already dirty bit is set and you are in the modified state, you are having that block and no problem. But if it is earlier was, you are kept it in a read purpose, then there is two possibilities are there. One, it could be that exclusive copy you are owning or you are having a shared copy. So the simplest possibility is the exclusive copy. That means you are only owning it, but you took it for a read purpose. Now you are trying to write into it. So what do you do? If you are having it in modified state, now let me think about modified state. That means you have already written into it and the data bit is already set. Then you just write into the data and keep it dirty, and you don't have to inform anybody because you are only owning it. Update the local cache value, and you don't have to go on main update the main memory also. No state change anywhere. Okay, and your state also doesn't change. You will remain in the main modified state only. But if you are having it in exclusive state, then your state changes, because earlier you are used for read purpose. Now you are writing it to the block, and main memory is anyway up to date till now. Now you are going to modify it. Once you modify it, you don't have to bother about keeping it in sync with the other copy. And since it is an exclusive state, you are only having it. The other cores are not having it. So you don't have to inform others. So you can just modify it, but you have to change the state of your cache line now to E block, E state to M. Okay, E to M. Now, what is the another possibility? Yes, you are in shared state. Now you know you are keeping it for a read purpose and it is being shared with the other core also. Now, what you should do? You want it for write to hit now. You want to write into it. Now, you can change your own state to S to E and make the other entries as invalid. Straight away to invalid. No other possibility of changing the other states to anything else. Okay. So, S to I, other cores, maybe one or two, maybe at least minimum one or many. All of them make it I, and your copy you make it into, update it and modify. That's all. Very simple, very logical. What are the changes to be done when you are your own copy is in different states? Okay, you have to imagine all different states. Now, write means. Write means what? Your cache block, wherever you want to write into it, that block is not there with you. That means you are not having it. But the same block could be anywhere else, and it could be in other caches. It could be in any of those states, but you are having it in invalid state. Okay? So now, no other copies are there. That means nobody is owning it. This block is nowhere there. Then it is very simple. You are trying to write into it, and it is not being kept in any other core. Then you take it from main memory, own it straight away, make it M, and keep it with you, and write the value into it. Value read from the memory, updated, keep it in M copy, done. Now, what is the other possibility? It could be in some other place in any of the states, M, E, or S. Correct? Now let us think. Other copies exist if only one copy in state E or more copies in state S. If it is only one copy in some other core, it could be in E state in that core, or it could be multiple copies on S in state in other cores. What you should do? Main memory is in sync with the these copies. Okay. Now what you do is value is read from the memory. Okay, you are right to read anyway. You know that if it is in M, E or S state in other cores, it is in sync with the memory. Memory is also having the same content. So you send a request saying that read with the intent to modify. I am now sending a read request saying that I am going to write into it. I am reading it for write purpose. That signal, special signal is sent. Now the snooping controller will know, okay, this core now wants to read the same location which I am, which is available in other cores in S or E state, but this guy wants to modify it. Now what you should do? You cannot allow this other cores to keep it in E or S state, make them all invalid. Snooping processes see this and set their copy state to I. Okay, set their copy state to I. Local copy updated and state set to M. Now your local copy is updated. Okay, you are you are getting the copy. You are reading from the memory, or it could be coming from the other places. It's same because all the available. You update it and make it into M. Okay, you take the value and then update it. Why you have to do that? Because when you are reading, When you are writing it, you may be writing a single particular byte or a word inside a block. Okay, but the modified state is with respect to the entire block. So you have to read the entire block and then modify the content which you are interested in. So local copy is updated and state set to yeah. That's all. Now, what is the other possibility? Another copy is there which is in M state. Now is the problem that another core is owning it and the memory is not having that value. So you have to get it from the other core only because the latest copy is available with the other core. But this core wants to know for a right purpose. So you have to make sure that that value, whatever is there in other core in the modified state, should be reflected in the main memory and given to the core which is right now asking for a right purpose. So you again send a request for a read with the intent to write. Okay, um, read with an intent to modify. Snooping process sees it, block that RWTM request, takes control of the bus, write back its copy to memory. The other core, which is owning it in the modified state, okay, takes control and writes the content into the main memory. Okay, we want to make sure that when one core is modifying it, earlier modified, and another core is going to modify now, that the earlier value has to be reflected in the main memory. And set its copy to I state. Now it is either I state because anyway you are going to give the ownership to the other core which is asking for it now. So make the original owner, earlier owner to I, and the original local processor reissues are no now this guy wanted it initially but it was blocked, right? It will again ask for it, and now no, it's now a simple no copy case. Okay, value read from the memory to local cache because now you are sure that it is not anywhere else. It is only this guy is going to own it, and it is taking from the latest value from the main memory and keeps it there. Local copy value is updated. When I say local copy, that is what is there inside the CPU. Okay, in the code. You read it and then modify only whatever value you are interested in. And then you have to keep it in M state because you are doing the right operation. So this is what is the entire scenario. All of this information can be described in one particular state transition diagram. Diagram shows what happens to the state of cache line in a processor as a result of memory accesses made by that processor, which is read hit, read miss, or write hit or write miss, or other operations which are happening as memory read operation, or read with an intent to modify, or invalidate operation, which is coming on the snooper bus. So snooping bus is giving these three signals, and the local processor is giving four signals, which is maybe a read or write, but which could result in a read hit or read miss, or write hit or write miss. So this is this validate, the transition diagram. I will just try to explain you. Suppose a local, this is a state transition as far as one CPU is concerned. Okay, I am just going to talk about, you know, invalid. Now, if the particular entry is invalid, that means it will go from invalid state to shared or modified state based on whether it is a write miss or read miss. Okay, it cannot be a read hit. Okay, okay, it can go into any of these three states based on the same block is available on some other core in what state. Now suppose I take this one. Okay, it means what? It is there in more than one core in a shared state, and this processor wants to ask for invalid. It is invalid means it is asking for a read purpose. Now memory read signal will be sent and it will go to shared state. Now it will also join the gang with the other two guys or two or more guys. And so if it is shared state, if there is a read hit is happening, it will continue to be the same. It will remain there. Similarly, you can see if it is invalid state and then it is asking for a read with the intent to modify, then you have to own it. No other processor can own it. So you get it, you modify it, the state of that particular entry is modified, and it will transition to modified. When what happens on other processors, you have to know based on what the state it is in. So now that I will show you in the next diagram. Okay, because this signal is coming to the memory. These are all what I am showing. This transition is based on the CPUs, local CPUs asking for a read or a write. Okay, you can see that read hit, write hit, and the write hit are there. Okay, and a write miss is there. only one place, only one write miss is possible, and then read hit read misses. So these, when these operations are happening from the local CPU, this is a transfer state transition, and the whatever signals are given is a what is the signal given on the bus. When you send the signals over the bus, other caches are reading it and they change their state. Okay, that based on this transaction, which is the signals which are sent on the bus, and then the reaction to that with the changes to the cache is given in the next diagram. Now imagine you have a memory read signal coming from the snoop, no, some other bus, some other guy, some other core wants to do a read operation. Okay, and you are owning it in a modified state. Now what you should do, someone wants to read it and I am keeping it in modified state. I should keep it, I should copy this value into the main memory, and then I should move my state to shared state. That's what I said. So this is what is copy the value into memory and go into shared state. Now suppose I am having it in exclusive state, I am getting a memory read operation. That means what? I am owning it exclusively for myself. Now someone wants to read the same data. What I should do? I should also, I can maintain it in the shared state. I don't have to invalidate it, but I cannot say that I own it now exclusively, because someone else also wants to do the read from the same location, same block. So I move to shared state. What if I am having it in a shared state already and I get a invalidate information? Can you tell me when this can happen? I am having it in shared state and somebody is invalidating it. This could happen only when someone wants to write into it. They want to own it. They want to change your own state to the modified state. So I should give up my ownership. Either I am having it in shared state, or whether I am having it exclusively for read purpose, or I am having it in modified state. I should give it back the control. Okay, I'll go back to invalid state. But when I go from modified state to invalid, I will write also the data and then go to invalid, my own entry. Whereas in other cases, I'll just move to the invalid state. That means because main memory is up to date and somebody wants to own it now, so I cannot now keep it in exclusive state or shared state, so I go to invalid. So this is very, very intuitive and very interesting state transition. Okay, it's easy to understand. So this I leave it as a exercise for you. This you can read it out and understand it. Okay, I think I have explained it very well in the transition. You have to view it again to, in case you have doubts, and we can use it. When we meet face to face, I can clarify some of the doubts you have. But go through this video first and then ask for doubts in the class. Now, I'll just quickly complete the directory-based protocol. See, what is the problem with the snooping protocol? Whatever your operations you are doing, you are going on broadcasting to everybody and then informing other caches and making it invalid or making it shared, or no, you change the states of other things. So this cannot be possible to do it if number of processes in the system are more. It's not scalable. So what invention or what the next level of innovation done here is the directory based maintaining the cache coherency. Okay, that means a state of each of those blocks is maintained as a directory, and then they are done at a point to point communication, not as a broadcast to all the caches, which is very time consuming and therefore power consumption as well as time performance wise is very difficult to implement it if the number of caches that you need to manage are more. So the directory based protocol came up, and then it is maintaining at a very abstract level, and it does it in a specific particular course only, or communicated, not the entire broadcast. You are maintaining the information about which are the cores are having it, and then the interconnect is also very complex. Okay, snooping is not like a simple broadcast network. It may be point to point connection like a ring or some other configuration wherein the same information is maintained at the directory level. Okay, maintaining a directory. Okay, in each of the cores are having a directory of information about which are the blocks are there, what states they are in, and mostly we are using the same state, that information that no, we are having it in MESI protocol, but we are abstracting it in a different level, and implementation is little more efficient than what you saw it in the snooping protocol. Okay, So the same shared, uncached, modified states are there. I'm not going to go into the details of this, and we are not looking at it in detail about the transition like what we did for MESI. Okay, if you understand the MESI and MSI protocol, you understand the the crux of the cache coherency, and that is enough to understand any other future protocols or directory based protocol in the implementation. Okay, so that's brings us to the end of this lecture. I hope it was useful and you understood the concept. Bye bye.